Hey everyone, Mr. Ahmed here. So I thought I'd make this video to go over the last two lessons that we're going to be covering in the calculus content in Première. Those last two lessons are 5.7, so the graph of f prime of x, and 5.8, which is optimization. Okay. Now, I guess jumping right in this first lesson, so the graph of f prime of x, the idea is to figure out how we can draw the graph of f prime of x based on just the graph of f of x. Okay, so essentially you're not given any equations. You're not told at all. Y equals 3x squared or something like that, and from that you could kind of differentiate that and then kind of figure out what the second graph, your differentiated graph, is going to look like. So we're not going to do that, but instead what you're going to do is you're going to actually inspect the graph of f of x. Okay, and then you're going to draw the graph of f prime of x based on that. Okay, so hopefully that's kind of making sense, but I guess you'll see here in a second here. Okay, so how do we do that? How do we draw the graph of f prime of x from f of x? Okay, well, the way this works is, first of all, realizing that, and just recalling, because you should already know this, that f prime, right, when I take f and I differentiate it and I get f prime is in fact an expression for the instantaneous rate of change at any point x on f of x. Okay, so to be clear, essentially, let's see if this is in what color are we using here? Here we go. Okay, so essentially, I know that if I take this point, oh, that's way too large. Let's make that a little smaller. Okay, let's say I've got a point right here, and I want to figure out what is the instantaneous rate of change at that point. In other words, what's the slope of the tangent, really, right? What's the slope of that tangent, right? Well, we know that the way that we figure out that slope of the tangent is by determining an expression for f prime, okay, and then plugging in x into that expression for f prime, right? And then that output, what you get here as a result, is going to be the instantaneous rate of change. Okay, so essentially, the instantaneous rate of change is actually something that we can use, like on f. So the instantaneous rate of change is something we can use on f that is going to help us actually, graph out f prime. Okay, so for example, I know here that I'm just going to randomly throw a number in here. Let's say, for example, that this slope here is 3. Okay, and let's say that the slope here is 2. And let's say that the slope, like just right here, is like 1. And then we know that the slope right up here, well, that's a horizontal line, right? That's a tangent line, right? The tangent line there is a horizontal line. That means that slope here is 0. Okay? So technically, all I have to do on f prime is just, well, I know that f prime is literally just an expression for the slope at x values. So for example, I'm going to try to draw a straight line here. I don't know how well I'm going to do this, but there. If the slope at that point of if the slope of the tangent line at that point here is 3, then that means that corresponding x value on the graph of f prime, the y value is 3. Okay, so here the y value is 3. Okay. And I'll say that one more time. Okay, so for this one right here, we said that the slope of the tangent line was like 2, I think. Okay, if at this point on f, the slope of the tangent line is 2, then that means if I take that x value and I plug it into the expression that corresponds to f prime, okay, I'm going to be getting a value of 2. Okay, so that means that on the f prime graph, this x value, the output is going to be the slope of the tangent line. Okay, so for this x value on the f prime graph, the output is the slope of the tangent line. So that means that the y value here is going to be 2. Okay, and so that's kind of the first thing that we realize, is that when we go from f to f prime, the slope on f in fact corresponds to the y value on your differentiated graph. Okay, so when you differentiate, right, when you differentiate, so I take this graph and I differentiate it, I go from f to f prime, what is the slope, the instantaneous rates of change at these many points? those slopes become the y values, right? At this x value right here, okay, it doesn't matter what the x value is, but I know that at on this x value, the tangent line is horizontal. That means the slope of that is 0, okay? And that's why, oh hey, check this out. That's why this is a root, okay? So at this x value, the horizontal line is 0. Sorry, the horizontal line has a slope of 0. That means on your f prime graph, if I were to plug in x equals 0 into that f prime expression, and then, sorry, x equals 0, x equals a random number. If I just plug in whatever that x value is into that f prime, I'm going to get f prime equals 0, okay? And that's why it's a root. That's why this maximum right here is in fact a root on f prime, and that's this second bit right here, okay? So your maximum and minimums, right? Your maximum and minimums, those have, right, those instantaneous rates of change at those maximums and minimums. In other words, the slopes of the tangent lines at those maximums and minimums, those slopes are 0. And so, because they're 0, those correspond to roots on the graph of f prime. Okay? Okay, so minimums and maximums are roots. Okay? Now, let's take a look at what happens here. Okay, well, what happens here? Well, let's check it out. I know that here, for example, can I scroll down here? I don't think I can. No. Okay. Well, I know that, for example, what's happening in this bit right here is that, you know, my slope is, so I'm going to do that again. Okay, so I know, for example, that here my slope was at 3, 2, 1, 0. I know my slope is going to be decreasing here. So my slope is -1, like -2, maybe it's like -3 over here. Let's say the slope right here is -4. Okay, this is the steepest part. Okay, if this slope here is -4, okay, and I think I had said it, this was like, you know, like, what was that? 0 as a -1, -2. -3. These are all just the slopes of these tangent lines, okay? And the slope right here is at -4. Well, this is my point of inflection, right? So this point of inflection is essentially the steepest part in this area right here. This is the steepest line, or the steepest part of this curve in this area right here, right? Because here I can see that my slope is going from 0 down to -1, -2, -3, and then this is going to be my steepest part. So let's say that's -4. But then now my curve goes from being concave down to concave up. So that means that my slope is now shifting. It's not going to keep going down anymore. It's now going to start increasing. Okay? So here I go from -4, so now the slope maybe is like -3, and then the slope like over here is -2, the slope over here is like -1, and then the slope here is 0, and then the slope here is 1, and so on. Okay? So this is actually, so when you read this, right, remember, your slopes on f become your y values on f prime, right? Your slopes on f become the y values on f prime, okay? So when I read this, I say, oh, okay, well, you know, like my slope here was -1, -2, -3. Okay, so my y values are going down. And they go down until a minimum of -4, so a point of inflection, which is where the slope is the steepest, okay, so -4. And then, because it goes from concave down to concave up, my slopes are now increasing, right? The slopes are now going from, you know, like -3, -2, -1, 0, 1, 2, 3. Okay, so after that -4, I'm going back up on this f prime graph, right? So the slope here could be -3, -2, -1, 0, right? That corresponds to the slope of this tangent line right here. Okay, that's going to be 0. Okay, and then, you know, 1, 2, 3, and so on, 1, 2, 3. Okay, so what we realize from this is that your points of inflection on your graphs in fact correspond to maximums or minimums. Okay, so points of inflection correspond to maximums or minimums. Okay, and then we can actually, I think that's really essentially like what you really need to know. But you know, when you kind of start putting that stuff together, maybe what I'll do is I'll actually erase what's up here. When you kind of start putting this stuff together, you kind of realize that you can come up with the rest. Maybe not number 6 just yet, but with numbers 4 and 5, right? Where you have where the graph of f is increasing. Okay, when the graph of f is increasing, well, that's a result of positive slopes, right? The slopes here are all positive, right? Like I said, this was like a slope of 3, a slope of 2, a slope of 1, all the way over here. All of these are positive slopes, and that means those are all positive y values, okay? Now, we'll notice that those positive y values, they're positive, but they're decreasing, okay? So for example, the slope here we said was what, 3? And we said the slope here was like 2, and the slope here was like 1. Maybe the slope right here is like 0.5 or something. And then the slope right at your maximum right here, we know now that that slope is 0, right? Okay, so here what you'll notice is that the gradient is positive, but it's decreasing. So we're going from 3, 2, 1, and down to 0. So there you go. Okay, so when your graph of f is increasing, that corresponds to positive y values on the graph of f prime. Because when it's increasing, those slopes are positive. Okay? Okay, so when the graph of f is increasing, the slopes of the instantaneous rates of change at these many points, okay, the slopes of these tangent lines, they're all positive. And we know that those slopes are in fact the y values on f prime. Okay, that was the first thing we realized. Okay? Okay, so the increasing part of your graph corresponds to positive slopes. That means it's going to be positive y values on the graph of f prime. Okay, now when you move on from that, okay, so let's take a look at this next section. What's happening here? Well, what's happening here is that actually throughout this entire section, the slopes, so the tangent lines that I can draw at any of these points, any tangent line that I can draw here in this little area right here, okay, any of those tangent lines has a negative slope. And because it has a negative slope, that means that its value f prime is negative. Okay, the value of f prime is negative for those, right? Because those negative slopes correspond to the y values on f prime. Okay, and so essentially what you realize is that whenever your graph is decreasing, whenever the graph of f is decreasing, okay, well, that means all your slopes are negative. That means that that corresponds to negative y values on the graph of f prime. Okay? And then again, we're back to increasing here, right? So here, this is increasing. The slopes here are positive, so my y values are positive. Okay? Okay, let me erase that. So we are essentially through 1, 2, 3, 4, 5. So we've talked about these first 5. We'll talk about number 6 in not too long here, but I do recommend that maybe you jot this down in your notes. I think when you come back to study this maybe over the summer or next year in Terminal, it'll be useful to have this information down. Okay, so essentially here what I'm saying is the gradient is positive, but it's decreasing, right? We saw our slopes were positive, but they were slowly decreasing, right? We went from a slope of 3, 2, 1, and so on. Here, remember that this is where f prime of x equals 0, right? Maximum and minimums, right? We figure out stationary points by setting f prime equal to 0 and solving, right? So f prime is equal to 0, at these points right here. And once we figured out that they're stationary points, right? Remember that just because it's a stationary point doesn't necessarily mean it's a turning point. You have to double check that it's a turning point by just making sure that the sign of the slopes change on either side, right? This right here is a turning point. It is a maximum because the slopes on the left-hand side, that means f prime, are all positive, and the slopes on the right-hand side over here, these are all, again, f prime, these are all negative. Okay, so here, like I just said, f prime is negative and is decreasing, right? We're going from -1, in terms of the slopes, -2, -3, and then we went down to like -4 for the point of inflection. Okay. Now this slope right, or this part right here, this is still so f prime is still negative here. Okay, f prime is still negative, but your slopes are now increasing. So although the slopes are negative, so you're still in the negative part of your of the y-axis, or you're in the negative part of the y-axis, right? The slopes are still increasing though, right? Like we're going from like -3, -2, -1, -0.5, right? So the slopes are negative, but they're increasing, okay? And then finally here, the slopes are positive, right? And they're also increasing. Okay, so the slopes are positive means that they're up in the positive y part of your sorry, they're up in the positive y values. Okay, as well, the slopes are increasing. So there you go. The slopes are increasing. They're going up. Okay. Okay. And then obviously remember that your point of inflection, that is going to be, like I told you here, because we're going from concave down to concave up, right? That's going to be a minimum. Okay, it's going to be a minimum. And remember that points of inflection, you can figure those out by setting f double prime of x equals to 0, right? And finding those out. Okay. Okay, so that was a lot of theory for this first page here. But yeah, you don't really need to worry too much about this little bit right here. You could probably ignore that, and you'll be just fine. Okay, so I'll just delete that. Maybe unhighlight this. There we go. Okay. And then you can also use f prime, okay? So you can use f prime, and then you can go and figure out what is the graph of f prime going to look like. Or sorry, the graph of the derivative of f prime, okay? Well, the derivative of f prime is f double prime. Okay, so what's that graph going to look like? Okay, well, I mean, you can kind of do the same thing again. You can, and this is what I call the numerical method, right? You can kind of attribute values to the slopes and sort of see what's happening. Right? So I know that, for example, the slope here, this is a slope, it's negative. Let's say it's -3. Oh, geez, this again. Okay, I'm going to change that. So -3. Let's say the slope here is -3. And the slope over here is like -2. Oh, actually, maybe that was a little too quick. Slope here is -3. Let's say the slope here is -2. The slope here is -1. The slope here is 0. The slope here is 1. The slope here is 2. The slope here is 3, and so on. Okay. So I can see, so remember that your slopes, when you differentiate a graph, right, those slopes become y values, okay? Those slopes become y values, all right? So, well, what does that mean? Well, this just means that if I were to draw this as a graph, it's down here, but just kind of walk you through it. Okay, so I start out at a y value of -3, and I go to a y value of -2, and I go to a y value of -1, and then I go to y value of 0, and I go to a y value of 1, and 2, and 3, and so on. Okay, so you can see here that your slope, okay, the slopes are in fact increasing throughout this entire thing, okay? And that's why the graph looks like this. Okay, so maybe I'll erase this right here. That's why this looks like this. Okay, now notice that everything before this minimum right here, which we know from up here was the point of inflection. Okay, so everything before that, right? The rate of change, so the slope of f prime here, those rates of change, those were all negative. Okay, those slopes on this part right here of your graph, those are all negative slopes. Okay, so that means those are all y values of f double prime. Okay, so all those y values of f double prime, they're all negative. And guess what? That makes sense, right? Because we saw that when f double prime is less than 0, that means that our graph is concave down. Okay? All right, I'm just trying to scroll down here. There we go. Okay, so that's kind of what we have here. Okay, so when you look at this, well, f double prime of x is less than 0, right? We said it was like -3, -2, -1, all the way down to 0 here. Okay, this is your point of inflection. Okay, and well, that makes sense because your graph is concave down, right? Look at your graph; it's concave down here. Here, your graph is concave up. That means f double prime of x is greater than 0. That means this should be positive on the graph of f double prime of x, and as we can see here, it is. Okay? And then finally, the point of inflection, right? Your point of inflection on f became a minimum point on f prime. And guess what? Well, maxes and minimums, if you differentiate one more time, those become roots, right? And it makes sense again, because here we said we had a graph or a slope of -3, -2, -1, 0, 1, 2, 3. Those slopes, they all become y values on the next differentiated graph. Okay, so they become y values on the f double prime. Okay, so again, maximum and minimums become roots. So this is really interesting to see, right? Because your point of inflection became, so your point of inflection became a maximum, or sorry, a minimum, right? It became a minimum over here. Okay, whoopsie. Okay, so it became a minimum over here, and then that minimum became a root in the graph of f double prime. Okay, so there you go. Okay, so maybe take a quick second just to kind of jot this stuff down. It's going to be really handy for you when you take a look at this later over the summer or next year when you're studying for your final IB exam. Okay. Alrighty, so now let's talk about stationary points of inflection. Okay, now we've already talked about stationary points. We know that stationary points are where f prime equals 0. Okay, and we know that points of inflection are where f double prime equals 0. And so a stationary point of inflection, well, that's just, a point where f prime equals 0 and where f double prime equals 0. So it's actually a combination of both. So it's a combination of a stationary point, and that stationary point also happens to be a point of inflection. And I already showed you guys this example last class, right? So we talked about that in the previous lesson, and I showed you guys that a stationary point of inflection looks like this, right? And the most basic way to get this is through the graph of f of x equals x cubed, right? If I were to differentiate this, right, I get 3x squared, okay? Well, f prime equals 0 in 3x squared when x equals 0, okay? Okay, so at x equals 0, f prime equals 0. And if I differentiate it one more time, at x equals 0, f double prime still equals 0, okay? So that's how I get it, that's how this point at x equals 0, that's how that point is both stationary because of this, right? Because you get f prime equals to 0. And it's also a point of inflection because of that, because f double prime of 0 equals to 0, okay? And so what's interesting here is that your stationary points of inflection, honestly, so you probably already saw it over here, right? Those correspond to roots in both f prime of x and f double prime of x, right? But you can kind of notice that yourself, right? Like when you think about this, just do the numerical method, right? Like, what would be the slope of this right here? I'll make this a little smaller. The slope of this guy right here could be like, 3, 2, 1. The slope right here is 0. And then check this out. The slope's actually increasing still, right? So you're still going up to like 1, 2, 3. Oh, okay. So when you go and take those slopes and you put those down as y values on the graph of f prime, okay, well, 3, 2, 1, 0, 1, 2, 3. Okay, so a stationary point of inflection becomes a minimum on f prime, okay? And also on the graph of f double prime, right? And by the way, it's sorry, I said it was a minimum, but it's also a root, right? Because here you go into 3, 2, 1, 0, right? So you're going onto the x-axis. So this right here is a root of 0. So this is one of those graphs that those curves that just touches the x-axis, okay? And so there you go. You've got a you've got a root on the x-axis, okay? Yeah, hopefully that was clear. I think I might have kind of confused you guys a little bit here, but essentially what's happening is that you've got slopes of like 3, 2, 1, 0, 1, 2, 3. This bit right here, right? This guy right here, that is in fact a y value of 0. Okay, and because it's a y value of 0, that just means that is a root on your x-axis, right? It just touches you. So this just touches the x-axis. Okay. All right. So hopefully that's clear. And then finally, if you were to take that and graph it, one more time, or sorry, differentiate it one more time, right? Okay. So this slope right here is -3, -2, -1, 0. 1, 2, 3, and so on. Okay, so there you go. And then those again become the y values on the graph of f double prime. Okay, so you're going -3, -2, -1, 0, 1, 2, 3. Okay, so that's going to be that graph that we saw earlier, right? It's going to be the one, whoopsie, the graph going up like this. Okay, where there you go. It's also a root on f double prime. Okay? All right, so hopefully that little bit here is clear as well. Okay, so stationary points of inflection, okay, those are going to be roots in both f prime of x and f double prime of x, okay, and they're going to be roots in f prime of x, okay, by being just roots that just touch your x-axis. They don't go through the x-axis, okay, they just touch it. Okay, so same thing here. Here, for example, your gradient is, let's say, -3, -2, -1, 0, 1, 2, 3. Okay, okay, so -3, -2, -1, 0, 1, 2, 3. Again, it just touches the x-axis. Okay, okay, so hopefully that is clear. All right, so the following example contains 3 stationary points. The third one is a stationary point of inflection. This is totally an example that I would, that I could definitely ask you on the test, asking you to, based off of f, draw the graph of f prime and then draw the graph of f double prime. Okay, and again, the way you do that is exactly what we've seen so far, right? I do recommend that you memorize this little bit right here. Okay, so memorize these rules, I guess. They can come in handy, but also, let's say, for example, you've forgotten to memorize those rules on your test. Well, what you can do is you can just use that numerical method that I've been kind of showing you, right? Right here you could say, the slope is like 3, the slope right here is like 2, 1, 0, -1, and then minus, let's say this is -2. This is a point of inflection right here. This is a point of inflection, so I'm going to be careful for this. I'm going to put a point right here. Let's say my slope here is -1, 0, the slope here is 1, 2. Oh, looks like I've got another point of inflection right here. I'm going to say that's a slope of 3, and then I'm going to keep going, going down here. So 2, 1, 0. Oh, okay, so here I've got my stationary point of inflection, and then now I'm going up to 1 and 2. Okay, so now doing this numerical method is really easy, because now I can literally just go and put those on my graph, and that's going to tell me sort of what my graph is going to look like, right? Okay, so I've got 3, 2, 1, 0. Okay, so 3, 2, 1, 0. -1, -2. Okay, this is my point of inflection. Okay, this is my point of inflection, so this guy right here. Okay, and at my point of inflection, well, this is a minimum, right? My slope is the lowest it is here at that point of inflection. It's the steepest as well, right? Okay, that's -2, and then my slope starts going back up to -1, and then here I've got a minimum, so that's a slope of 0. Okay, so I've got another root. Okay, so I have this root right here, and I've got this root right here. Okay, so 0, 1, 2, and then I identified I had a point of inflection right here. Okay, that point of inflection I said was 3. Okay, that means it's going to be a maximum over here, right? That 3 is going to be a maximum because I'm going, from 0, I'm going 0, 1, 2, and then 3, and then I'm going back down to 2, 1, and back down to 0. Okay, so back down to 0 here. So this guy right here. Okay, and so when I go and put that, that's going to be my little root right here, and then my slope goes back up to 1 and then 2 and so on. Okay, all right, so hopefully that's kind of clear. And remember, like here you can see that this is a this right here is going to be a maximum, right? Because the slope here was 3, so that's your y value. This is a maximum. Here we know that these are minimums, right? They're going to be, and those are minimums that are occurring right on our x-axis. So those are roots that occur right on our x-axis, right? They can also be maximums, by the way, that occur on the x-axis, but right now the most important thing is that these are roots that occur on the x-axis, right? So if I know that this is going from 2, 1, 0, 1, 2, that tells me that this is a minimum. So that means that actually, so if I've got a maximum over here and I've got a minimum over here, right, then that means that this forcément goes from being concave down because of this maximum to being concave up because of this minimum, right? So that means I've got something of a point of inflection somewhere around here, okay? Okay, so hopefully that helps. And then again, you do the same steps going down to this, right? So you can still do, a slope, using this slope method, right? You can still say, -3, -2, -1, down to this guy right here. This guy would be 0, right? That would be a root right here, okay? And then 1, and then 2, and then this is a point of inflection, right? This is a point of inflection that I had identified on here, so it's also a root, right? That guy becomes now your maximum, and so on. Okay, so just applying the same steps again, but now down to f double prime. Okay. Okay, I just don't want this to take too long, so I'll let you maybe take some time right now, maybe pause the video, practice this, try to see if you can go and actually draw the graph of this, the graph of f double prime based on the graph of f prime. Okay, it's the same steps that I did going from f to f prime. Okay, it's the same steps. Okay, and then I would also recommend that you do example 1 from your practice problems right now, because example 1 is actually going to be asking you to graph f prime and f double prime. And again, use that numerical method that I was talking to you about and that I was showing you. That's kind of what I have up here. All I did is I wrote down some slopes. Okay, those slopes helped me, identified some points of inflection. Those slopes helped me draw the graph of f prime, and then again, I do the same thing from f prime to go down to f double prime, right? I'm going to write down some slopes, and then I'm going to use those as y values in f double prime. Okay? So yeah, so maybe take a minute here to try your hand out at drawing these, and of course double checking, that minimums become roots, that points of inflections become maximums or minimums, and so on. Essentially, checking this. Okay, so make sure that you're checking this out as you work through those practice questions. Okay. Okay. Now the next bit is, how do you go backwards? Okay, so how do you go from f prime of x to f of x? Okay, and okay, so you could technically memorize this if you really want to, but you really don't need to, because remember, the y values in f prime of x become your slopes in f of x, right? When we were going from f of x to f prime of x, the slopes became the y values, okay? Right? But now if I'm going backwards, well, the y values on f prime of x are the slopes of f of x. Okay, so when I look at this, okay, so let's say that this is f prime of x. And what are these y values? So right now what I'm going to write is I'm going to write down y values. Okay, well the y value down here is going to be like, -2. This guy right here is going to be -1. This y value is going to be like 0. This y value is going to be 1. And this y value is going to be like 2, for example. Okay? Okay. Well, these y values are in fact slopes. Okay, so, these y values are slopes on f of x. Okay, so how would I draw this? Well, let's see. I've got a slope of -2. Maybe that looks something like this. I've got a slope of -1. Then I've got a slope of 0. And then I've got a slope of 1. And then I've got a slope of 2. Okay. As you can see, right, this is looking like it's curving up. This is a minimum right here. Okay. So this root right here, this 0 corresponds to a minimum. You can do the same thing down here, right? That's why I'm telling you this numerical method is probably a lot easier than it is to try to memorize everything and be like, okay, what does that look like again? Again, just write down the slope. So a root like this corresponds to a max. How do I know? Well, because I know that the y values on this correspond to the slope. So this is f prime of x, right? So the y values on f prime of x correspond to the slopes of f of x. So let's say this is 2. I'm going to say this is 1. I'm going to say this is 0. This is -1 and -2. Well, guess what? A slope of 2 looks something like this, right? A slope of 1 looks something like this, right? A slope of 0, a slope of -1, a slope of -2. Well, there you go. You've got a parabola facing down, okay? And so this point right here is a maximum. That root right here is a maximum, okay? And so that's what I do here, okay? Just for the sake of time, I maybe what I'll do is I'll let you guys kind of work through this, but the idea is still the same, right? Here, it's just that you're going backwards. That's it, okay? So I know that the y values on f prime correspond to slopes on f, okay? So what I'm going to do is I'm going to write down the y values of f prime, so 4, 3, 2, 1, 0. These are y values on f prime, -1, -2, -3. Maybe this guy's like, -3.5 or something. Then, -3, let's say, or -2, -1, 0, 1, 2, 3. So all I did is I wrote those y values down, and then I go and draw what would that look like. Those y values, because I know their slopes, what would those look like for f? Okay, well, you know, a slope of 4, right? A slope of 4, always the same problem. You know, a slope of 4, a slope of 3, a slope of 2, a slope of 1, a slope of 0. Okay, so this root right here is my maximum. A slope of -1, so roughly something like this. A slope of -2, -3, and this is going to be the greatest slope, right? The steepest slope, not the greatest, sorry, the steepest slope. And then now I'm going, my slope is actually increasing again. So now I'm going, you know, like maybe like something like this. So -2, -1, and then now I'm at 0. Okay, so this guy right here is a minimum, right? This guy right here is a minimum. This guy was a maximum, right? This steepest slope right here, you probably identified that. It's a point of inflection, right? Okay. And then you just keep going, right? So slope of 1, a slope of 2, a slope of 3. Okay, a slope of 1, a slope of 2, a slope of 3. Okay, so there you go. That's kind of how you get that. All right. Okay, so hopefully that is relatively clear. Make sure you're dropping by, you know, the office hours if you've got questions, or if you've got questions, send me an email and I'll be more than happy to answer. Okay. So that's the first part of this lesson. So if you're okay with that, and you're just going to wait for me to teach you optimization, you know, in person when you get here, that's great. I'm going to go ahead and move on and continue teaching optimization in the same video. I'll just quickly check the length of my video right now. It's 36 minutes. I should be okay. All right. Okay, so optimization problems are actually really, really interesting, because this is kind of where you start seeing, you know, real life applications of calculus. Okay, optimization is essentially about taking like a real life situation, okay, modeling it using some expression or some equation, okay, and then trying to find either the maximum or the minimum of that equation. Okay, because usually what happens is that you can actually, what are you looking for in this real life situation? A lot of times you're looking to, like, you know, maximize profits, or you're looking to, you know, minimize the length of material required, right? Maybe you want to maximize cost, but maybe you want to minimize time or stuff like that, right? So if you're able to come up with equations, right, that represent the situations that you're dealing with, well, you can differentiate those equations, right, to get, you know, f prime, okay, and then you set f prime equals to 0. That's what I've got right here, right? You set f prime equals to 0. Why? Because you're looking to find those stationary points, right? And once you've found the stationary points, then you have to just make sure that those are either your maximums or your minimums, right? Okay, so maybe this will sink in when we take a look at some of these examples. So here, example 1, among all the rectangles of perimeter 20, find the one of the maximum area. Okay, so maximum area, as soon as you see like that word, maximum or minimum or something like that, that's 100% going to be an optimization question. Okay, so that's kind of a keyword that you can be looking out for. But essentially, okay, so among all rectangles of perimeter 20, okay, so maybe I'll just draw a rectangle. Oh, actually, it's right down here. There's a rectangle, you know, well, perimeter 20. That means that, you know, if one side is x and the other side is y, then the perimeter of this is going to be 2x plus 2y, and then here it's equal to 20. Okay, so equal to 20, so that's what I have right here. Okay, find the one of the maximum area. Okay, so I know that area is just going to be x times y, which is, you know, that's equal to area. Okay, well, this is great, because now I've got two equations. I've got an equation for perimeter, and I've got an equation for area. And what I'm trying to maximize is I'm trying to maximize area. Okay, so what I'm going to do is I'm going to take this bit right here, which is the perimeter equation, right, simplified. Okay, I've isolated for y. Okay, I'm going to substitute that 10 minus x in place of y in my area equation. The reason I want to do that is because I want to have a nice area equation where I only have one unknown, and that's what I get over here. Okay, so this is now the area. Okay, so all I did right now is I took the perimeter equation, isolated for y, substituted that into the area equation. Why the area equation? Because I'm going to try to maximize that area. Okay, so you're probably already kind of cluing into this, right? Because this is a quadratic, right? And this is a parabola that's facing down, right? It's facing down because of this negative right here. Ah, okay, so this is what this is. It is this. Okay, so this is a parabola where the y values are area, and the x values, well, the x values correspond to this length right here. Okay, so what I want is I want to figure out this point right here, because at that x value, right, whatever the x value is here, that is where my area, my y value, is at its highest point. That's where my y value, my area, is a maximum. Okay? And so the way that you do that, right, how do we figure out maximums and minimums using f prime? Remember, well, you take f prime and you set it equal to 0. That gets you your stationary points. And then you have to go and double check, okay, are those stationary points turning points? Okay? So I get the derivative of g prime. Okay, I get the derivative of the area, which I call g prime. Okay, so the derivative of that is going to be negative 2x plus 10. Okay, I set that equal to 0, and I get x equals 5. Okay, so this is a stationary point, and like I was telling you guys, you have to double check, is this a turning point, right? Sorry, I'm using my notes here just because, I don't know, I found they were a little clearer perhaps, but I don't know. Maybe you prefer using Christos's notes, totally up to you. But essentially, so we got x equals 5. This is a stationary point. Is it a turning point? Remember that you can check this using one of two methods, right? To see if this is a turning point, and then figure out what type of turning point is it. Is it a maximum or a minimum, right? And the way you do that is either by using the first derivative test, okay? And remember that the first derivative, all you're going to be doing is you're going to be choosing points to the left of x equals 5, right? And then you're checking, for those x values, are the slopes positive or negative for points to the left of x equals 5, right? Well, if I choose, for example, so this is my g prime equation right up here, okay? So, and I know that x equals 5 is a stationary point. So let's say, for example, I use 0. So x equals 0. X equals 0 is a point to the left of x equals 5. Well, if x equals 0, g prime equals 10. Okay, so g prime is positive. Okay? Okay, so there you go. That means, when g prime is positive, that means that the slope is positive. That means that your graph is increasing. So, okay, so that means that your graph is increasing. That's what I have over here. Your graph is increasing. Now, to the right of 5, okay, well, to the right of 5, let's say 6, 7, 8, 9, even 10, doesn't matter. Let's say 6. Negative 2 times 6 is negative 12. Negative 12 plus 10 is negative 2. G prime is negative. When g prime is negative, right, that means that the slopes are going down, right? The slopes are facing down. The slopes are decreasing. Okay, so instead of this, you don't have this. You've got negative slopes, and when you've got negative slopes on a graph, that means that your graph is decreasing. Okay, that's why it's decreasing here. That means that you've got a maximum at x equals 5 because it's increasing. Your graph is increasing to the left, and it's decreasing to the right. So a maximum at x equals 5. And there you go. That answers your question, right? Well, actually, does it? Not quite, because the question was what? Find the one of the maximum area. Okay, so I know that maximum area occurs when x equals 5, and y equals 10 minus x, so y equals 10 minus 5, so y equals 5. Okay, so maximum area occurs when x equals 5 and y equals 5. Okay, and that's what I have over here. So that maximum area is 25. Okay, now using the second derivative test, you could have also checked that this x equals 5 was a maximum. Okay, so the way that you do that is just getting the second derivative. So the second derivative is just negative 2, right? The derivative of negative 2x plus 10 is negative 2. And then it doesn't matter what x value you have, right? It doesn't matter what x value you have, because g prime is just always going to be negative. And when g prime is negative, sorry, g double prime is negative. When g double prime is negative, that means that your parabola is facing down, which means that you've got a maximum at x equals 5. Okay? All right, so that was that first example. Let's take a look at the second example. Okay. I do recommend that you, maybe at this point, actually, maybe I'll go through example number 2, and then maybe I'll let you guys, not I'll let you guys, but I would recommend that you guys try out examples 3 and 4, and I don't remember how many examples there are, but we're going to go through all of them. Maybe try those out first on your own, and then see if you can get to the answer, and then maybe come back and watch the rest of this video here. But anyways, among all the rectangles of area 25, find the one of the minimum perimeter. Okay, so this is interesting. So I want rectangles that have an area of 25, but I want the minimum perimeter. So this is actually, it's interesting in the sense that you could totally apply this to like a real life scenario, right? Like you could be like, okay, well, you know, I'm looking for a rectangle. It has to have an area of 25, and I want to be using the least. Let's say I want to make that like a some kind of fencing. Okay, I'm trying to make fencing for I don't know, a chicken coop or something, and I want that chicken coop to have an area of 25 meters squared, but I also don't want to use too much material, so I'm trying to minimize the material that I use, right? So there you go. There's a real life scenario that you can answer using calculus, using optimization. Okay. Okay. So among all rectangles of area 25. So here's your rectangle. The area is 25. So x times y is 25. Find the one of the minimum perimeter. Okay. Well, I know that the perimeter is still, you know, 2x plus 2y equals, you know, perimeter. Okay. Except now what I'm going to do is, because I'm trying to minimize perimeter, I'm going to take this area function equation right here. I'm going to isolate for y. Right? I'm going to isolate for y, okay? And I'm going to substitute that into my perimeter equation. Why? Because I now have a perimeter equation that only has one unknown, right? That perimeter equation only has that one unknown now, right? So this is what my perimeter equation is. So this is perimeter equals 2x plus 2 times 25 over x, which is just 50 x to the power of negative 1, okay? And then the reason I wrote it like this is because now I'm ready at this point to, well, I'm trying to find a minimum of this. That means I need to go and find, you know, what is a stationary point. That means I need my first derivative. Okay, so I'm going to get the first derivative of this. So I'm going to get 2, and then I'm going to bring this negative 1 down here. So negative 1, so the negative 1 drops, and then I subtract 1 up here in the exponent, right? So this becomes 2 minus 50x to the power of negative 2. Okay. Or, you know, minus 50 over x squared, okay? And then I set this equal to 0 because I know that's where my stationary, because I know that stationary points occur at 0, okay? Sorry, not occur at 0. Stationary points occur at p prime equal to 0, okay? So then I want to figure out, okay, well, what x values would yield, you know, p prime equal to 0? Okay, so then I solve that, right? So I set that up. I say 2 minus 50 over x squared equals 0. Okay, and then I'm going to bring over the 50 over x squared over onto the right-hand side. I'm going to multiply by x squared on both sides. I'm going to subtract the 50. I'm going to factor out the 2. Okay, so I'm at 2, and then x squared minus 25 equals 0. I'm going to factor this. When I factor this, I get x equals 5, and I get x equals minus 5 as potential roots, okay, from my factors. Okay, except, you know, remember that x is in fact a length. Okay, so it wouldn't actually make sense for us to have x equals minus 5. Okay, or is it a length or a width? It doesn't matter. Let's say it's a width. Here I say it's a width. Okay, so this right here is a width, so I can't have x equals negative 5. You can't have a negative width, so I'm going to ignore that. Okay, I'm going to stick with the x equals 5. Okay, okay, so what I'm going to do is I'm going to figure out, okay, is x equals 5 a turning point, right? Because right now all I did is I figured out that it's a stationary point, but I got to figure out, okay, is it a turning point as well? And I have to also figure out, you know, is it a minimum as well, right? Because that's what we're trying to do. We're trying to minimize perimeter. So I'm trying to see, is my perimeter really a minimum at x equals 5? Okay. So again, you can use your first derivative test or the second derivative test. Okay. If I want to use my first derivative test, all I'm doing is I'm saying, okay, well, at x equals 5, so x equals 5. Okay. I'm going to be looking at, or using this right here, okay? And I'm going to be using x values that are to the left of 5 and to the right of 5 to see what happens to p prime, okay? Well, to the left of 5, let's say this is like, I don't know, 2, okay? Let's say it's 2, I can't say that. Let's say it's 1. That's going to make it easier, okay? So to the left of 5, let's say x equals 1, okay? Well, 1 to the power of 2 is 1. 50 over 1 is 50. So this is 2 minus 50. That's negative 48. That's negative. Okay, so p prime is negative to the left of 5. And then to the right of 5, let's use, I don't know, 10. Let's use x is 10. Well, when x is 10, 10 to the power of 2 is 100. So 2 minus 50 over 100. That's 2 minus 1/2. Oh, okay, so, well, that's 3/2. So that's positive. Okay? So there you go, that's positive. So we see that the graph is decreasing before x equals 5 and is increasing after x equals 5. That means that you've got a minimum at x equals 5, and there you go. That means that x equals 5 does yield a minimum for the perimeter. Okay, you could have used also the second derivative test. Okay. The second derivative test means that you would have taken this guy right here. Where is it? This guy right here, you would have differentiated that. Now this is 2 minus 50 x to the power of negative 2. Okay. So you're going to bring down that negative 2 down to in front of this guy right here. So that you're going to have negative 2 times, negative 50. Okay, that's going to be a positive 100. And then x to the power of negative 3. Okay. So positive 100 and x to the power of negative 3, which is 100 over x cubed. Okay, and then all you have to do is now you just have to figure out, okay, well, at x equals 5, is my graph concave up or concave down? Well, I know that it's, when x is equal to 5, 5 to the power of 3 is 125, so 100 over 125, okay, that's positive. Okay, so p double prime is positive, and we know that when it's positive, your parabola is going to be facing up. Okay, so because it's facing up, that means that you've got a minimum at x equals 5. Okay, so what was the question? The question was, among all the rectangles of area 25, find the one of the minimum perimeter. Okay, so the minimum perimeter occurs when this guy here is 5, and therefore occurs when y is also 5 as well. Okay, so that's what I have right here. Okay, so the minimum perimeter is therefore 20, because you've got 5 plus 5 plus 5 plus 5, so that's 5 times 4, which is 20. Okay? Okay, let's take a look at example number 3 now. At this point, I do recommend that you just pause the video, try this out on your own, and see if you can figure it out. Okay? This one's a little trickier though. So here's how it goes. So you want to construct a rectangular fence for an area of 24 meters squared. Okay, I can already write an equation. X times y equals 24. Okay, that's an area. But the cost for the material of the front side, so I'm going to say this right here. Let's say this is the front side. Sorry, this right here. Okay, let's say this length right here is the front side. So this x length right here is the front side. Okay. Oopsie, no, that's not what I wanted to do. Okay. So if I want this to be $10 per meter, and then the cost for the material of the other 3 sides is $5 per meter, find the cheapest solution. Okay, so I've got to come up with an equation for the cost. Okay. Now I know that the front side has a length of x, and I know that it costs $10 per meter. So that means an expression for the cost of just the front side is 10x. Okay, but the remaining 3 sides all cost $5 per meter. That means that this side right here costs 5y. This side right here costs, sorry, not sure if you can see, this side right here also costs 5y, and then this side right here costs 5x. Okay, so an expression for the total cost is just going to be the sum of all these costs, right? So 10x for the front side, plus 5y plus 5y plus 5x, which is what I have over here. Okay, so I group my like terms together. I get 15x plus 10y equals the cost, except I'm trying to find the cheapest solution. Okay, so that means that I have to minimize the cost, which means that I have to get an expression for the cost that only has one variable in it. So what I'm going to do is I'm going to take this equation right here for the area. I'm going to isolate y, so y equals 24 over x. Okay, and I'm going to substitute that in place of y in my cost equation. Okay, so now I have this new equation, 15x plus, when I substitute this in here, I get 240 over x, which is this bit right here. Right, it's this is the same thing. This is now my cost equation that only has and contains one variable, and I want the cheapest solution. That means I'm going to try to minimize that cost. Okay, so I'm hoping to get a minimum with this. Okay, all right, so the first step is going to be obviously to get the derivative of the cost. Okay, so cost prime or C prime. Okay, then I want to figure out the stationary point, so I set that up equal to 0. Okay, so when I set that up equal to 0, I get 15 minus 240 over x squared equals 0. Move the 240 over x squared to the other side, bring up the x squared, multiply both sides by x squared, factor out the 15. So I get x squared minus 16 over here, which I'll factor into x minus 4 and x plus 4. Okay, except again, remember x is a length. It does not make sense in this situation to have x equals negative 4. I can't have a negative length, so I'm going to ignore that. Okay, I'm going to keep moving with x equals 4. Okay, now at this point I can use my first derivative test or I can use the second derivative test. It's totally up to you guys. At times maybe the second derivative test might be faster, So essentially what I'm going to try to do is I'm going to try to show that what's happening here is the following, right? Using my second derivative test, I'm trying to, oh geez, this again. I'm trying to show that this is happening, okay? Trying to show that this right here is the case. And the reason why I want to show that is because I want to show that this is in fact a minimum, right? So here, I'll scroll down a little bit here, okay? Now, the way that this happens, okay, the way that this happens is by, first of all, getting the second derivative. Okay, so that means I'm going to bring down the negative 2. So negative 2 times negative 240 is a positive 480. And then that's x to the power of negative 3. So that's 480 over x cubed. And then I'm going to check at x equals 4, which I know is a stationary point. Okay, at x equals 4, is my curve, or is my parabola concave up? Okay, and well, it's concave up when when cost double prime, or the second derivative is greater than 0, right? And it is, right? When you've got 4 to the power of 3, right? That's 4 times 4 times 4, that's 64. 480 over 64, that's going to be positive, right? So because it's positive, that means that it is concave up, which means that we do have a minimum cost when x equals 4. Okay. All right. So the question here was asking us find the cheapest solution. Okay. So the cheapest solution involves getting x equals 4. Okay. And if x equals 4, then based on the area, y equals 6. So there you go. Wait, what was the question asking? Find the cheapest solution. Oh, okay. Okay. So they want also, like, the actual cost. Sorry, my apologies. They want the actual cost of this. So what would be the cheapest cost? So the cheapest cost here is obtained when x equals 6 and when y equals sorry, what was it? X equals 6? No, it was when x equals 4, I think is what we had. Yeah. Yes, when x equals 4. So when x equals 4 and when y equals 6, right? So you're going to just plug that into your cost formula, right? So 15 times 4 is 60, plus 10 times 6 is 60, so that comes out to 120. So actually your cheapest solution is going to be 120, okay? So there you go. All right, let's take a look at this example right here. So consider the region enclosed by this and the x-axis. Okay, so this one is rather challenging. So I would say for sure, if you haven't stopped the video by now, stop the video. Try this question out and then see if you can come up with an answer on your own, and then come back and watch the remainder of watch the solution. But essentially, here I've got a rectangle. It is inscribed within this region. That means it's found within the region that is enclosed by the x-axis and y equals 9 minus x squared. Okay, so essentially I'm trying to say, what is the largest area? Okay, well, I know that I have to maximize the area of this rectangle, which means I have to come up with an equation for the area of this rectangle. Okay, all right, so how do I do that? Well, let's see. I know that my rectangle, right? It looks like not looks like, it is. It's going to be symmetrical, right, about the y-axis. Okay, it's going to be symmetrical about the y-axis because, well, 9 minus x squared is also symmetrical about the y-axis. Okay, that means that any length over here, right? So any length that my rectangle extends into the first quadrant is the same equivalent length that it extends into the second quadrant, right? So this length right here and this length right here are indeed the same. Okay, so maybe I can call that length x. Now here they decided to call it a. It doesn't really matter. I'm going to call that length x. Okay, I'm going to call this length x. And if this length right here, just from here to here, is x, then that means that the length from here to here is also x. That means that the total length of my rectangle is 2x. Okay? All right, now that's great and all, but I'm like, okay, well, how do I figure out the height? Well, this corner of my rectangle is actually found on y equals 9 minus x squared. So if I were to write down the coordinates of that point right here, okay, if this length right here is x, that means the x value here, let's say it's x, okay? They decided to use A. It doesn't really matter. Okay. Now, if that's x, that means that the y value of that coordinate, well, that's 9 minus x squared. There you go. Okay, so there you go. That means that this height right here could be considered to be 9 minus x squared. Now, maybe I don't know, maybe if some of you are confused, maybe it does help to use a different value, or sorry, a different variable than x, because you might be like, wait, how is this 9 minus x squared? Because, you know, this entire thing is 9 minus x squared. And like, I totally get that. You can use a different variable if you wanted to call this a, right? If this is a, then the total length here is 2a, okay? And if this is a, then that means your x value is, well, a, right? Your rectangle is going up to a, extending to a horizontally. And then all you have to do to get the y value is you just plug in a in place of x, right? So 9 minus a squared, right? So you still end up with the same thing, okay? But essentially what you realize is that the length of your rectangle is 2x, and the height of your rectangle is 9 minus x squared. So you can come up with an area, and then the rest of this is all the same steps. Okay, so really quickly walking you through this because I don't want this to be too lengthy. Oh geez, I say that and it's 1 hour, we're 1 hour in. But hey, not bad for a 2-lesson video, I'd say. Okay, so I'm going to move relatively quickly here, but essentially you've got the area equation. You are going to get the first derivative, so differentiate that. Why? Because you're about to set that up equal to 0, because you're trying to find the stationary points. Okay, so I set this equal to 0. I don't show it here, but I do. I should have had a, you know, that equals to 0. Okay, now when this equals to 0, well, that happens when x equals plus or minus square root of 3. Okay, we're going to ignore negative 3, square root of 3 for the same reasons. Okay, like if I want a is out here. I'm trying to figure out what a's value is or what x's value is. It's positive. So I'm only going to concentrate on this bit right here. Okay. And then I can do either the first derivative test or the second derivative test. The second derivative test here is, I think, easier because all you have to do, so what is this? Here, find the rectangle of largest area inscribed within that region. So that means I'm trying to find the maximum area. Okay, so that means I'm trying to show that my parabola is looking something like this. Right? And the way that I do that is, so it's concave down, right? So the way I do that is by using my second derivative test, right? And what I can do is I can just take this, get the second derivative, which is negative 12x, okay? And then when x equals positive square root of 3, right? Doesn't matter, you know, positive square root of 3, doesn't matter what it is, but, you know, a positive times a negative. Okay, that means that a double prime is going to be negative, okay? So that means that my graph is concave down, okay? And because it's concave down, that means I've got a maximum value. Oh, geez. I don't know why. That means I've got a maximum value right here. Okay, so that's what we've got. So what the question was asking was find the rectangle of largest area. Okay, so I know that the largest area occurs when x equals square root of 3, and I've got this right here. So then I just plug in x equals square root of 3 in this and solve. Okay. What was it? Find the rectangle of largest area inscribed. Okay, so it's not actually asking for the area. I think it's asking us for the dimensions. So find the dimensions of the rectangle of largest area, blah, blah, blah. Okay, so we know that x equals square root of 3. So the length here was 2x, so 2 times square root of 3. So that's 2 square root of 3. And then this is going to be just 9 minus square root of 3 squared, which is 9 minus 3, which is 6. Okay, so your rectangle measures 2 square root of 3 by 6 and has therefore an area of 12 square root of 3. Okay. Okay, and then the last example, and I do definitely recommend that you pause the video and try this example out on your own before continuing. But this example is definitely a little trickier than the other ones. Okay, so a swimmer is at point A inside the sea. So you're inside the sea here, 3 kilometers away from the beach. Okay, so this is the beach right here. She wants to go to point B at the beach, which is 5 kilometers away. So from point A to point B is 5 kilometers away. From point A right to the beach, like, you know, perpendicularly to the beach is 3 kilometers. And we're also told that, let's see, what else are we told? We're told that the length between C and B, horizontal length, I guess you could say, is 4 kilometers. We're also given that, okay? And when she swims, she covers 1 kilometer in 30 minutes. Okay, so I translate that into 2 kilometers per hour. When she runs, she covers 1 kilometer in 15 minutes. So I can translate that into 4 kilometers per hour. So figure out the time she spends when she swims directly to B. Okay, so from A to B, she travels 5 kilometers. Okay. At a speed, now this is in the water, right? So at a speed of 2 kilometers per hour. Find the time she spends. Well, I know that, geez, this is my bane. All right, so I know that d equals tv, right? I know that distance equals time times speed or velocity, however, well, distance equals time times velocity. I'm gonna say that one more time. Distance equals time times speed. Displacement equals time times velocity. Okay, doesn't matter in this case, but so here what we're trying to do is we're trying to find the time. That means I'm going to isolate for t. So t is actually distance divided by speed. Okay, so she's got to travel 5 kilometers. So 5 kilometers divided by the speed, which is 2 kilometers. Okay, that means it would take her 2.5 hours. So 5 divided by 2 is 2.5. 2.5 hours or 150 minutes. No, that's if she swam directly to B. Okay. Now the time she spends when she swims to C and then runs to B. Okay, so if she goes from A to C and then decides to run to B, how much time is that going to be? Well, okay, to go from A to C, right? Well, A to C is a distance of 3. Okay, and then she's also swimming that distance, which is 2. So 3 divided by 2, that's the time. So 3 over 2 hours, which is this bit right here, plus. And then she travels 4 kilometers by running at a speed of 4 kilometers per hour. So plus 4 over 4, that's going to take her 1 hour, right? It takes 1 hour to travel 4 kilometers if you're traveling at 4 kilometers per 1 hour. Okay, so you've got 1 hour plus 1.5 hours. So that's going to also take 2.5 hours. Now, maybe you're thinking, well, to get from point A to point B, I guess she could either just decide to swim straight to point B, or she could swim from A to C and then run from C to B, and it's going to take her the same amount of time. So it doesn't really matter. There's no optimization to be done here. But there is. There is optimization to be done. Okay? There is a point between C and B where she could aim for that would actually make it so that she could minimize the time it takes her to get from point A to point B. Okay, so the minimum time she can achieve if she swims first to some point D between C and B and then runs the rest of the way. So that's what I drew over here. Okay, so I think this is going to be probably the hard bit. It's kind of like if ever you're given this question, I think the hard bit is just kind of coming up with with this equation that represents the time. Right, because we're trying to minimize that time, right? So when we're trying to minimize that time, that means we're trying to show this, right? I'm trying to figure out what x value gives me this. It gives me a minimum time. Okay, so coming up with the equation is going to be hard. So here's how I do it, right? Like I say, okay, well, if she's maybe I'll zoom in on this. So if she's traveling to a point D between C and B. Okay, I don't know what that distance is from C to D. I'm going to call it x. But I do know that the total distance from C to B is 4. So that means that from D to B, okay, so from D to B, that distance is going to be 4 minus x. Okay, and I know that this triangle ACD is a right angle triangle, right? This is a right angle triangle right here. Okay, this is perpendicular to AC is perpendicular to BC. Okay. And so I can actually come up with a distance for this bit right here as well, right? I can come up with an expression for the distance for this bit, right? I'm using the Pythagorean theorem, right? 3 squared plus x squared, and the square root of that gives me this, okay? And this distance right here I have is 4 minus x. Okay, so perfect. So I have a distance that she spends swimming in the water, and I have a distance that she spends running on land. Okay? And I want to get the time. I want to get an expression for the time for this, and I want to minimize that. All right, well, we know that, like I said, the time is distance over speed, right? Okay, so distance over a speed of, and what was it again? It was in water, it was 2 kilometers per hour. So this divided by 2 gives me the time it takes her to go from A to D. And then the time it takes her to go from D to B is this distance, 4 minus x, divided by 4, which is the speed that she runs at on land. Okay, so it's going to be this divided by 2 plus 4 minus x divided by 4. That's going to be an expression for the time, and I want to minimize that. So there you go. That's the bit that I've got right here. Okay, and okay, for the sake of not taking too much longer here, essentially what you're doing is you're doing the same steps. Okay, you are going to try to well, when you look at this, what I did is I in fact decided to maybe simplify this out a little bit. I'm actually just getting it ready to differentiate it, right? So 4 over 4 is just 1, minus x over 4 is minus 1/4 x, right? And now that it's set up like this, it's kind of ready to differentiate. Now, mind you, don't forget about this. You're going to have to actually use the chain rule on this one, right? Because this is 9 plus x squared, all of that to the power of 1/2. So you bring down to the power of 1/2, and then you subtract 1 on in the exponent here, so you get this bit right here. Okay, so 1/2 minus 1 is negative 1/2. Okay, but then remember, you have to apply the chain rule. So you've got to multiply by the derivative of 9 plus x squared, which is 2x. Okay, and the derivative of this guy is just negative 1/4. Okay, so then when you do that, you get this, and then you get that. All you're doing is you're just simplifying. This is 2x over 4, so there it is, 2x over 4. This guy right here is a square root in the denominator because this is negative to the power of negative 1/2, so there it is, minus 1/4. And I want to get the stationary points. That means I have to set this equal to 0, and then I have to solve. Okay, all right, so I set it equal to 0. Okay, so I get this. I multiply both sides by 4. That means I can get rid of these 4's down here, so I get this bit right here. Okay. And then I can multiply by that. There's a squared missing here. I think it's just the scanner didn't pick it up. But I multiply by this, and it comes up here. Okay, I multiply both sides. It comes up here. Now I'm going to square both sides to get rid of the square root. So I get 4x squared equals 9 plus x squared. There's a squared missing over here, so just to be clear. Oh, haha. I caught it before it happened. There. Okay, and then I'm gonna group my like terms. I'm going to get the x squareds together on one side. That's 3x squared equals 9. That means x squared equals 3. That means x equals plus or minus the square root of 3. I'm missing a little bit here from the scanner. Now, obviously, for the same reasons as before, we're going to ignore x equals negative 3, because if we go back up here, what was x? It was this distance right here. It doesn't make sense for us to just have this as a negative distance, so we're going to ignore that. We're just going to focus in on x equals positive 3. And again, you can use this. You can do this either using the first derivative test or the second derivative test. It really doesn't matter. Let's just use the first derivative test. So that's what I've got down here. So when I want to use the first derivative test, I'm going to go back up to this guy right here. Okay, so this is my expression. Okay, and I'm picking a point to the left of square root of 3. Okay, so a point to the left of square root of 3, well, it doesn't matter what point I pick, but let's pick 0 for simplicity's sake, right? If I pick 0, right, well, this becomes 0. So 0 over, it doesn't matter what this is, right? This is going to be 0 over 4 times square root of 9, so this is actually going to be 0 over 12, right? It doesn't matter what that is, because that's 0. 0 minus 1/4, okay, so t prime is negative. Okay, so it's decreasing. So it's decreasing, okay? And then to the right of this, now I'm going to pick a point to the an x value to the right of the square root of 3. Now, this would be nice if this were a 25, because then I could just square root that 25 and then I get a value. Yeah, let's do that. Let's try that. So I'm going to pick the way that this becomes a 25 is if I pick the square root of 16. Yeah, I'm going to pick the square root of 16. So I'm going to pick 4. Okay. So I'm going to pick x value of 4, which is bigger than square root of 3. Okay, and so 4 times 2 is 8. 8 divided by 4 is 2. Okay, so that's going to be 2. Maybe I'll write that down. So 2 over, and then this is square root of 9 plus 16. And I did that on purpose because I wanted this to be a square root of 25. And the square root of 25 is just 5. So this is 2 over 5 minus 1 over 4. Well, 2 over 5 is 0.4, and 1 over 4 is 0.25. So the answer here is actually 0.15. That means that it's positive. Doesn't matter what that answer is, but it's positive. 2 over 5 is bigger than 1 over 4, so t prime is positive. That means that it's going to be going up, so it's increasing. Okay, so there you go. We just showed that we get a minimum at x equals square root of 3. Now, what was the question? the minimum time she can achieve if she swims first to some point D. Okay, so that means you're going to take that x equals square root of 3, you're going to plug it into this, and you're going to get an answer. Okay, so when you do that, that's what I do here. Okay, I feel like I wouldn't say this is a calculator question. I just kind of gave you this, but you would just go and simplify this as best you can. Okay, and that would be pretty much it. Okay, so there you go. That is the last 2 lessons of calculus. So hopefully that was helpful. All right, that's it, guys. Take care. Bye bye.